part 3 of the presentation, we're really going to move from the abstract to the concrete and talk in great detail about how to make a library with the new Kapa HyperPlus kit. So remembering all the principles that we discussed before, that the aim is to make the highest possible quality library with whatever library construction methodology you choose, how you can optimize different parameters, but really getting into the nitty-gritty of doing it. And you'll see as we go through this workflow, although we've shared a lot of information, there's actually very little that you need to optimize in the end. And so at this point, it may sound like a daunting task, but it really is actually a pretty simple workflow, very easy to do. People that have no prior experience with library construction can easily try this for the first time and have success. Having said that, if it's the first time you try a kit, any kit, never use precious samples. Like always try and do your upfront evaluation and optimization with what we call a non-precious bulk sample. So take a sample that's either commercial DNA or DNA that's representative of what you're going to be processing. But never ever, it doesn't matter how good a kit is, how well it's advertised, never use it for the first time on something that you can only make one library of. And so going straight into the summary of this presentation, we're going to talk a little bit about just the key features and benefits of the kits, what applications it can be used for, what's in the kit and what pack sizes are available, and then we're going to go into the detailed workflow, going step by step, talking about the critical parameters, those few things that can be optimized, and then ending again with some in-process QC and just some real examples of data. So the features of the benefits of the kit, it's an integrated enzymatic fragmentation library construction protocol. So both the elements of library construction, namely fragmentation and the addition of adapters are catered for. It's a very flexible kit, so it can be used for a very wide range of inputs, so from a nanogram to a microgram of DNA. It's compatible with all kinds of different types of DNA, so low complexity DNA, high complexity DNA. You can use it for human genomic samples, FFPE samples, PCR products, cDNA. And just on the second page is sort of a summary of the applications and the input. So as we discussed previously, the recommended input depends a little bit on the sample type, the sequencing application, the amount of sequence space that you're interrogating, and the depth of sequencing that you need to accomplish. And so for whole genome sequencing, it's anywhere between 15 nanograms to a microgram, dropping all the way down to anything over a nanogram for amplicons and full-length cDNA with some variation in the middle. So a very versatile kit, compatible with pretty much all sequencing applications that require fragmentation and the addition of adapters through a ligation process. What's great about it is that the whole process is automation friendly. None of it needs specialized equipment other than liquid handling if you're going to go that way. But you don't need special tubes, you don't need special equipment. Essentially, the whole protocol can be completed with a set of pipettes and a PCR instrument. As was needed, to make high-quality libraries, we needed to build an enzymatic fragmentation reagent that doesn't suffer from some of the drawbacks of existing things out on the market. So we managed to build a reagent that allows you to tune sizes. You can shear DNA down to 150 base pairs, or you can make relatively long insert libraries, sort of on the limit of what can be handled in Illumina sequencing. So insert sizes around 600 base pairs, which kind of gets you to that size that's just optimal for cluster, or that can still be utilized during cluster amplification, so just less than 700, 800 base pairs. It's very robust, the fragmentation process, so it's really not that sensitive to input DNA. If you're going to digest or fragment a microgram of DNA versus a nanogram of DNA, yes, you will need a little bit more time to fragment the microgram of DNA, but the mode sizes end up being in very similar places after similar times. And whether, if you have two samples and one has double the amount of DNA than the other, it's not going to be a problem. It's very reproducible. So one thing about not only the fragmentation reaction is very reproducible because it's so easy to set up and there's no handling issues. Once you've got the optimal parameters tuned in and you use the same instrumentation and the same types of tubes and things, very, very predictable outcome. But also because you don't have to recover DNA from Covaris tubes, for instance, and go into library construction, you just carry on in the same tube. We find that the results from this process is a lot more reproducible. So by the time you get to amplified library, when you make replicates from the same thing, those library yields end up being right on top of one another. And we did this experiment very recently where a few folks in R&D make replicate libraries from the same thing. So we had 3 different people starting with the same input and making 2 or 3 different libraries. And when you do this with Kavara sharing, for instance, by the time you end up with amplified library, it's common that one library can have double the yield, or 25% or 50% higher yield than the other. But with this protocol, we're seeing very, very, much more reproducibility because there's just so much less handling, and it's so easy to do. So far fewer places where you can lose DNA in the process. It to date is the kit that we've developed that supports the highest efficiency of library construction. So it is input dependent, but it doesn't matter what you start with. Your chances of getting adapter ligated library, and as much as possible adapter ligated library, is best with this kit. The kit contains, like all our library preparation kit, contains HiFi, which is our evolved enzyme, high efficiency, high fidelity, very low bias amplification enzyme, and then we supply the primer mix to ensure that your amplification is as efficient as possible, and so that you can limit the number of amplification cycles together with really high library construction and really high library construction efficiency and high amplification, very optimized amplification parameters. You can ensure that you do as little amplification as possible. And then just, I'm not going to show a lot of data. Unfortunately, we don't have time for all of that in the scope of this presentation, but we will present a lot of data at AGBT this year, showing that the nature of libraries prepared from enzymatically fragmented DNA is similar to the nature of DNA prepared from Kavara shared DNA, using the same library construction chemistry, and so the enzymatic fragmentation is unbiased. It doesn't. There's nothing per se about enzymatic fragmentation that we're really concerned about. And because combined with the HyperPrep chemistry, in this integrated workflow, we're actually getting libraries that's either similar in quality or even better in quality than libraries prepared from Kavara shared DNA, because you're just losing less unique molecules along the way. So we skip past the application. So what do you get in the kit? Essentially, there's 3 types of components in the kit. We have 1 enzyme and 1 buffer for every enzymatic step. So there's a fragmentation buffer, a fragmentation enzyme mix, and then it contains, to complete out the fragmentation part of it, there's a conditioning solution in there. And this is used when your DNA samples contain EDTA, and we'll speak about that in huge detail still. Then as far as the library construction part goes, we have 2 enzymatic steps, so a combined end repair A-tailing step, for which there's 1 enzyme and 1 buffer mix, and then a ligation enzyme and buffer. And then we have the library amplification enzyme, so it's already a ready mix that has everything in it except essentially the primer, which comes in a separate tube. Just note that this amplification primer mix is based on the P5 and P7 flow cell sequences, so only suitable for amplification of libraries that have a full-length adapter at the time of amplification. It is possible to use your own primer mix if your adapter design is different, and we'd be very happy to share the appropriate way of designing primers and formulating primers to ensure that you get the highest possible amplification efficiency with HiFi. What's not included in the kit are adapters, and then the spry beads. So there's only 2 cleanups in the kit after ligation and after amplification, but the spry beads are obtainable from Beckman Coulter. The kit comes in 3 pack sizes. So we have the 8 reaction kits. These are normally just test kits, so to allow you to get a small kit and try it out. Then the 24 reaction kits is for moderate throughput, and then the 96 reaction kits. These are automation friendly kits, so they do have higher overages than the other kits, because for automated library construction you typically have to robots aren't as accurate as people. They need larger excess volumes and waste volumes. And so 96 reaction kits are fully compatible with automation from that point of view as well. So here's just a little screenshot of the technical data sheet, which all of you have, and will also be available. So whenever you order a kit, you'll get a hard copy of this data sheet. It's also available for download from our website if you lose it for some reason, or you can always email support@Kapa Biosystems. We'll send you another one. And just to point out, so the first section of the TDS has a lot of what we call important parameters. So it has a lot of background information. A lot of the things that we discussed in this series of webinars is echoed here and summarized here, as it specifically pertains to this kit. So interesting reading, but you can skip straight through to so on page 11 there's a process workflow, just an overview of how you get very graphically from enzymatic fragmentation right to amplified library. And then there are two appendixes at the end. One is about size selection, so there's a detailed protocol for dual splice size selection, which we discussed in detail in part 2. And then also just looking at optimization of fragmentation parameters. It really explains a little bit more about how the fragmentation reaction works. And if you have, particularly difficult samples, different types of complexity samples, it gives you, a pretty good guide on how to optimize fragmentation parameters for any type of sample that you may want to process. So going through the workflow step by step. So the first, so we obviously set up the fragmentation reaction. Fragmentation then typically happens at 37 degrees. So there are instances where we would fragment maybe at 30 or 25 degrees, and we'll refer to that briefly. But your fragmentation time is going to be anywhere between 5 and 40 minutes, typically between 10 and 30 minutes. So for most inputs, 30 minutes is going to give you a mode fragment size around 200-ish, 150 to 200 base pairs, and 10 minutes will give you a mode fragment size between around 300, 350 base pairs, and that pretty much covers the range of most Illumina libraries that people make. Then, the 5 minutes is so you'll drop the time to get a larger mode insert size, so you fragment for less time. And so if you're really trying to make long insert libraries, you would reduce the time or then reduce the temperature so that the time doesn't become too short. And then, on the other end, we would, for FFPE samples, we sometimes have to fragment a little longer. After the fragmentation reaction, so this all gets set up on ice to make sure that the fragmentation reaction doesn't start prematurely or doesn't start for some samples before it starts for others. We do the fragmentation, so we go straight from ice to 37 degrees, straight back to ice or to a 4-degree block on a robot. You add the end repair and A-tailing mix, so you're going to pre-mix the buffer and the enzyme for end repair and A-tailing. Add that, mix it all up, incubate at 65 degrees for 30 minutes. You may remember that we said streamlined protocols typically have a 2-step process. For this integrated workflow, we just have to do the second part of that, so the 65-degree incubation. Then to all of this, so this is all still happens in the same tube in which you started your DNA with your DNA. You'll then add adapters, the ligation reaction mix. The standard ligation is 15 minutes at 20 degrees. This is where you do your first sprite cleanup, and the standard sprite cleanup is 0.8x to get rid of adapters and adapter drivers. If you have a PCR-free workflow, in other words, there's no reason to amplify. In other words, you have full-length adapters that have all the elements that you require for cluster amplification, sequencing, and multiplexing if needed. And if you have enough material at that point, that's where your workflow would end, and this would take you, somewhere between an hour and an hour and a half, depending on the mode fragment size that you're targeting. And you can go straight to target capture sequencing. In most workflows, there will be some library amplification, and this is just the standard amplification with Kapa Hi-Fi. After that, we do a 1x sprite cleanup, and then you have your final library. You can include size selection if you need it. So depending, again, on the application, the mode insert size, your sequencing read length, all of the things that we discussed previously, you can include a size selection step either using beads, which we describe in the protocol, or using electrophoretic system of your choice, either after the ligation cleanup. So the ligation cleanup has to be done first to get rid of the peg in the ligation buffer, or it can be done straight after library amplification. So the cleanup after library amplification is not essential if you want to go to size selection. You can do it, does no harm, but either way, if your application or sample type benefits or requires size selection, it can be incorporated at any of these two places in the protocol. Critical parameters, so starting with DNA, the only thing that's very important to remember about the enzymatic fragmentation, it is sensitive to EDTA. So enzymes that manipulate, DNA modifying enzymes typically need magnesium, and magnesium at optimal concentrations. If your samples include EDTA, it will chelate the magnesium, so reduce the effective magnesium concentration in the reaction and affect the activity of the enzyme. And so that's where the conditioning solution's there, and we go through a detailed example of how to use that. So that's the one thing that potentially has to be optimized. Other thing that's important is for consistency. So, once you've dialed in your parameters to get consistent results, is to do this transition from fragmentation into the NGS pair A-tailing incubation as quickly as possible and without delay. And so, keeping everything on ice, so you want to kind of slow down that reaction by putting it on ice, the fragmentation reaction, so that fragmentation doesn't continue, so don't leave the samples at 37 and don't leave them on the desk. Straight on ice or cool the PCR machine down. Add the NDP A-tailing mix as soon as possible and get it in the 65-degree reaction as soon as possible. That's pretty much the only trick in setting all of this up. Then as far as ligation is concerned, the only really parameter to make sure that you have optimal is the adapter insert molar ratio. Make sure that it's appropriate for your input. And again, there's a table in the protocol for low input applications. Definitely makes sense to play around a little bit with adapter concentration. And maybe at the very high end, but the table provides a really good starting point. There are some applications where you can maybe play around with ligation times, but I wouldn't worry about that. I would just basically use that as a very last resort. And then library amplification, always important to use the optimal number of amplification cycles. And you have two options here. Either use, there are some tables that provide really good guidelines, but also using some in-process QC, so post-ligation library amplification really allows you to do that very efficiently. In terms of QC, so very much the same as what we've discussed in previous parts of the series. So although the fragmentation reaction is much less sensitive to input DNA than, for instance, fragmentation and other enzymatic fragmentation methods, it is very useful to know what you start with. So for consistency, to know what you should expect, and also because if you want to sort of look at library efficiency, it is important to know what you really started with. And then again, for FFPE samples, there's definitely a correlation between fragmentation time and quality. And so using the Kapa human genomic DNA quantification and QC kit, that gives you a quality score for DNA, and is also very helpful, at least initially, to help optimize parameters. And then your final library, same as everything else, you're going to confirm the size distribution of the final library, and you're going to quantify by preferably qPCR to make sure that you've made the right size library. In other words, the adapters have ligated efficiently, and that you quantify so that you make sure that you have put the right amount of each library into the next stage of the process. It's the one thing that you will see what's absent is in this integrated workflow, we don't look at the outcome of fragmentation after the fragmentation reaction. So, typically after Kavara shear, most people would shear the DNA, then, run it on a bioanalyzer or something to see that it's sheared properly. With the integrated workflow, we essentially go all the way through to the end of library construction and then assess the outcome of fragmentation in the context of the final library. And there's a few reasons for not doing it. The first is it's really hard to take a small, say this is a 50 microliter reaction, to take a small aliquot like 5 microliters. It's possible to take it, but it's really hard to process it in a way that is representative of the final library. So there are ways that you can kind of stop the reaction, clean it up, run it on a bioanalyzer. By the time you've done that, you could have actually made the library. And we've looked at a whole lot of different strategies. There's some that's better than others of giving you a good idea of what the fragment size would be, but all of them have problems in terms of handling and being representative of the final library. And so for this integrated workflow, just make the libraries right through the end, and we tune the fragmentation times based on the libraries, and we'll go through a detailed example of how to do that. The only other in-process QC that, again, as we discussed before, that's really important, is to stop at the end of ligation and really look at how well did the core process work. So if we started with 100 nanograms of DNA, how much of that ligated library do we have at this point? And then because you know what you have, it's very easy to determine whether your library amplification, how many cycles you need to do, and then it allows you to assess whether your library amplification is as efficient as it should be. So let's start with a really practical example, and we're going to go step by step through this. And if you have questions, let's write them down, and we'll discuss them all in the end. So this is a practical example. Let's say we want to make some libraries from 100 nanograms of human genomic DNA. The DNA was extracted and it's now in TE buffer, so that's 10 millimolar tris with 1 millimolar EDTA. So first thing, we're going to quantify the DNA using qubit, which is the best, qubit or picogreen, same thing. That's the best way for quantifying double-stranded DNA. So these are just random sample names, and say here's the different concentrations. So the first thing we need to do, because our samples has EDTA in them, we need to normalize the concentration. So we need for samples containing EDTA, you need to dilute the samples into 30 microliters because we're going to need to add 5 microliters of conditioning solution. If your sample did not contain EDTA, you would make it up to 35 microliters from the beginning. So in this case, because we do have EDTA in the buffer, we need to dilute all these samples so that we have 100 nanogram, which is our input into library construction, in 30 microliters. And to keep we want to keep the EDTA concentration consistent at this point. So don't dilute the DNA in water or in another buffer. Just dilute it in exactly the same buffer that it is at the moment, so that we know exactly what the EDTA concentration is in the buffer at the time that the samples are correctly normalized for input. So obviously, depending on the concentrations, you'll use a little bit less or a little bit more of each sample to get to the 100 nanograms. But important, dilute them all to 30 microliters in the buffer in which they currently are in. Now the next step, because we do have EDTA, if we had no EDTA in the sample, we would just dilute the DNA in water or 10 millimolar tris, which is probably what it will be in at the time, to 35 microliters, and we'll skip this whole step about the conditioning solution. Since we have the EDTA, we now have to calculate what the final EDTA solution concentration is in the reaction. And so this is not in the DNA itself. This is once the DNA has been diluted out into the total 50 microliters. So to the 30 microliters, we're going to add 5 microliters conditioning solution, and then we're going to be adding 15 microliters, so 10 microliters of enzyme, 5 microliters of buffer. So at this point, what we need to calculate is not the EDTA concentration in the buffer, so it's not 1 millimolar. It's what it is once you've diluted the DNA, the input DNA, into the final 50 microliter reaction. And so in the buffer, it's 1 millimolar. You now have all your samples normalized to 30 microliters. And so once you've added everything else, the final EDTA concentration will be the 30 divided by 15 times 1, which is 0.6 millimolar. Then we go to the table. So this is table 2 in the TDS. It is very important. So because the reaction is very sensitive to EDTA, we have to balance the concentration of EDTA very carefully with the conditioning solution. If you add too little, it means you don't neutralize all the EDTA, and it will slow the reaction down. If you add too much, it means that you're going to neutralize the EDTA and supply, some activating reagents to the reaction, and it's actually going to speed up fragmentation, which may sound like a great idea, but can lead to huge inconsistencies in the future. And so it's important to know what the EDTA concentration is and then carefully balance it. And so what this table allows you to do, it sort of gives you a range of possible EDTA concentrations. And again, this is in the final 50 microliter reactions, not in the DNA itself. And then it tells you how to dilute the conditioning solution. And it's pretty much set up to just always make 100 microliters of conditioning solution. You need 5 microliters per reaction. So if you have less than 20 samples, you'll just make this. If you have more than 20 samples, then just multiply it so that you have enough. So if you're going to have 100 samples, then you have to make at least 5 times more. And so for 6 millimolar, you're going to make a 2.2-fold dilution of the conditioning solution, which is 46.5 microliters per 100 microliters, and you just dilute it with water. The reason we do this way, so normalizing everything and adding a fixed volume of conditioning solution, this is just to make setup easier, and also make eventually if you do move to an automated system, it's much easier to do this, do it like this, than trying to make a diluted conditioning solution for every single individual sample. So key here, if you have EDTA, normalize everything so that they're in the same EDTA concentration with your input, the desired input in your 30 microliters, make the appropriate dilution of your fragmentation solution, and just add 5 microliters to each. You mix that up, and so this all gets done on ice. So remember that this is an enzymatic reaction. You want to keep the enzymes most active at 37 degrees, and so by keeping everything cold, you're making sure that you're not starting the enzymatic reaction earlier than you think that it's starting, or earlier for some samples than others. And so your total fragmentation reaction is now 35 microliters, which is your DNA, the input DNA diluted to 30 microliters, plus the 5 microliters of EDTA, of conditioning solution, sorry. If you didn't have EDTA in the sample, you would just dilute it down to 35 microliters from the beginning. Then you're adding 5 microliters of the buffer and 10 microliters inline. These can be pre-mixed beforehand, but it has to be made freshly. So if you just wanted to dispense that in a single pipetting step, just before, once you've prepared your sample, make a quick mix. So if you have 10 reactions, you want to make around 150 microliters of the mix plus a little extra. Again, make on ice, keep it on ice, and then you're going to be adding 15 microliters of pre-mixed to every sample. Mix nicely. You can vortex and spin things like there's no components in here that can't be vortex. We use that all the time to make sure we'd rather vortex quickly, and spin down in a picofuge to make sure that things are properly mixed than sitting pipetting up and down hundreds of times. If you're using single tubes, it's easy to do that. If you're doing things in plates, then obviously pipetting up and down with a multi-channel pipette is better. And then you can set up your fragmentation incubation. So the reaction itself is very simple. It's basically just an incubation at 37 degrees. But again, to make sure that things are consistent, we'll pre-cool. So we set and it's best to do this in a thermocycler. You can do it on a heating block, and in automated solution, on automated systems, we do it on deck on heating blocks. You don't need a heated lid for this reaction at all. But for manual processing, it's much easier to control things when you put it in a PCR machine. So you set the PCR machine so that it's cooled at 4 degrees. So you pre-cool the block at 4 degrees. So your reactions are set up on ice. You put them in the pre-cooled machine and then let it run to 37 degrees. And then once you're done with the 37 degrees, so you're going to program it for the appropriate amount of time, and we'll talk about that now. But then just set it to cool down the reaction down to 4 degrees again to make sure that you slow down the fragmentation reaction basically to 0. Now, what about the fragmentation time? So here's a table that gives you a really good starting point. So if you want a really long insert library, then around about 5 minutes is going to be, it's going to be somewhere in a range of 3 to 10 minutes. As your mode fragment length drops, so as you're trying to make shorter and shorter insert libraries, the time increases. And so how do you go about figuring out what the best time is? When you try the kit for the first time, the best way to go, because we're not going to look at fragmentation independent from library construction. So the best thing to do is when you try the kit for the first time, set up 3 libraries. So you use exactly the same sample, take like a bulk DNA sample, set up 300 microliter reactions independently, then pick the time from this table that seems to be the most appropriate. So if you want to make a round about 300 to 350 base pair library, incubate the one replicate at 10 minutes, the one for 5 minutes, and the one for 15 minutes. And go all the way through library construction and just see where those things pan out. If 10 minutes is spot on, you're going to carry on with 10 minutes. If 10 minutes is a little long, then try maybe 12 minutes and 14 minutes the next time. And so, within 1 or 2 steps of making, 2 or 3 libraries at a time, you can very easily get to the optimal fragmentation time for your specific type of samples. Again, as I said, don't use precious samples the first time you try this. You may or may not get it right. And then the appendix contains a lot of good guidelines for more difficult samples. So this is a really good starting point for genomic DNA. But if you have FFPE DNA, you would do it a little differently. So with FFPE, essentially, you would use this as the minimum time. And then for your 3 samples, so you would do 10 minutes, 15 minutes, and 20 minutes. Rather than plus and minus 5, you would just keep on adding a little bit longer. Because we know for FFPE, because of the damage, it benefits from slightly longer fragmentation. And then if you have really low complexity samples, so things like cDNA and PCR products, sometimes, even at 5 minutes at 37, you're completely over-fragmenting it, so it's much too short. If you try and drop the times less than 5 minutes, it becomes really hard to control. And so what you can do for low complexity samples is drop the temperature to 30 degrees or 25 degrees. And there's some really good guidelines in the appendix of how to go about optimizing the fragmentation time, for normal samples when you try it the first time, or then for some of these, more difficult sample types. Okay, so now you've done your fragmentation incubation. So, remember the first or second time you do this, you're going to still play around with these times, do more than 1 replicate at different times. But once you've dialed in the time, so once you've figured out what works well for your sample, you're just going to do that straight every time, and you should get very reproducible results. Then we're going to do the NVP and A-tailing reaction. Very simple. So you now have your tube. So in the same tube or the same plate that you used for enzymatic fragmentation, it's been cooled down in the cycler to 4. You're going to put it on ice. You can premix the NVP and A-tailing buffer, same as for the fragmentation reagents. These premixes you can keep for a little longer, so you can actually, once you break out the kit, you can make these premixes and store them in, say, like aliquots for 3 or 4 libraries at a time. And there's some conditions or some guidelines at the bottom, so you can keep these mixes. For instance, for automated library construction, they don't have to be kept cold. They're okay at room temperature. If you're working manually, it's always good to work on ice. But these mixes for NVP and A-tailing and then for ligation too, the mixes can be made a little ahead of time and stored appropriately. But for fragmentation, it has to be fresh. So you start with a 50 microliter reaction. That's now the product from your fragmentation reaction, contains the DNA and all the fragmentation components. To that, you're going to add the NVP A-tailing mix. Now you have a 60 microliter reaction, and then you're just going to set this all up on ice, go stick it in the thermocycler. There's no reason, for you're putting that cooling step in here. You can if you want. It doesn't make really any difference. But the 65, you go straight to 65 degrees. And the 65 degrees does a whole bunch of different things. It inactivates the fragmentation enzyme, so it's now completely dead and no fragmentation can take place. And that's why it's important to go really quickly from the end of fragmentation to where you start this incubation step. It also kills the end repair enzyme, as you can remember from what we discussed from two-step or streamlined protocols. But there is some degree of end repair taking place. So as the reaction's ramping from 4 degrees to 65 degrees, the enzymes aren't completely dead immediately. So there's a bit of end repair taking place. With enzymatic fragmentation, the ends are less damaged than it is with Kavara shearing, and so we don't need a formal end repair step. And then, it's going to do A-tailing at 65 degrees. So that incubation has a lot of different functions in this protocol. And then, just so for 65 degree incubation, you need to have the heated lid on. We normally set the lid to about 85 degrees. So if you set it to 100 degrees, like the standard is for PCR, it heats the tubes up a lot. So if your cycler allows you, you have to use the heated lid. If it allows you to set the temperature of the lid, set it about 20 degrees higher than the incubation temperature. And then you can go down to 4 degrees. So you obviously do want to stop that reaction. You can go down to 4 degrees. If you think that you're not going to be there when it's finished and there's going to be some delay, like you're going on lunch or something, set it to 4 degrees. If you're going to be there immediately, then you can set it to 20 degrees because you're going to basically do ligation at 20 degrees. So then there's no real reason cooling down. It doesn't matter either way. If you're in doubt whether you're going to be there or not, set it to 4 degrees. The 20 degrees is more for automated protocols, where the robot will carry on immediately, and so for manual, 4 degrees is always safest. But important again, I can't stress this more for consistency. Set everything needs to be cold from the beginning of fragmentation to where you go into the 65 degree step, and try and do this as consistently as possible for consistent results. And then from here on, it's the standard HyperPrep protocol. So the front part of this protocol is really condensed now because it includes fragmentation and everything else. But from here, it's just the standard ligation and library amplification. So first step of the ligation reaction, and you can do this while the 30 degree incubation is taking place. The 65 degree incubation for 30 minutes is taking place. So again, there's a table that gives you the suggested adapter stock concentration for different inputs. And you can use this as is. The only 2 reasons you would optimize is for really high inputs. I would recommend trying maybe 10, 20, and 40. At 40 to 1 at high inputs, the adapter does become expensive. So see if you see if you see a benefit to it. It's worthwhile doing the experiment. At 10 to 1, we know that the conversion rates are at least 30 to 40%. So it's really high. If you want to get close to 100%, you're going to have to increase this a little bit. So for PCR-free workflows, for instance, this may be actually important, where you're not going to do any amplification and you need to get as much of that ligated library. And then for very low inputs. So if you're kind of in this range of less than 25 nanograms, maybe 10 and lower, try the 200 to 1, but try something like 400 or 500 to 1, and then 800 to 1,000 to 1. And again, see if using higher adapter insert molar ratios does give you a benefit in terms of conversion rate or library construction efficiency. But that's really, just grabbing the concentration off the table is a really good approach. The ligation reaction setup is very simple. So now you have your reaction. You're still in the same tube. So you started with 50 microliters of DNA. you had 50 microliter of fragmentation reaction, including your DNA. You had 60 after the end repair reaction. This is where you are now. And then we're going to be adding 50 microliters worth of stuff. So 5 microliters worth of adapter, and then the ligation mix. So that's the buffer and the enzyme, and there's a little bit of water in there. Again, this can be pre-made, and so you can dispense that as a single 45 microliter aliquot. And it's definitely, we do that for automation, it's definitely kind of recommended because it just makes fewer pipetting steps and more consistency. The only thing that's important about the ligation reaction is always add the adapter first before you add the ligase. If you do add ligase before there's adapter, the ligation enzymes are very, very active, especially in this kit, and they tend to ligate adapters to library inserts, so they're going to find something to do. And although the library inserts are 8-tailed and they're not a perfect match, you will get chimeric library fragments if you add ligase before adapter. And so always just add the adapter before the ligase. When you work manually, you can set this up on ice or on the bench, doesn't really matter. And then your standard ligation is 15 minutes at 20 degrees. Then we get to the post-PCR cleanup. This is, so you're still working in the same tube now for the HyperPrep chemistry because it's less prone to making adapter dimer. We do a single 0.8x cleanup, so that's designed the ratio is designed with the amount of PEG that's in the reaction at the time, designed to exclude adapter dimer. So you have a 110 microliter reaction at this point. You're going to add 88 microliters of ampere for that. So just note that this becomes a big reaction. If you're working in PCR plates, most of the PCR plates, the volume, the well is around 200 microliter working volume, so you're getting very close to the top of the well. If you're working in tubes, you can go to a bigger tube. It's very possible to do this reaction in a standard PCR plate, but just be careful because the volume here is very close to the top of the plate. And then we give a detailed protocol for the cleanup. It's essentially, you mix stuff, you bind it to the beads, the amount of time that you bind it to the bead. So this is just the incubation at room temperature. We say 5 to 15 minutes. If you have low input libraries, definitely go for 15 minutes. If you have higher inputs, anything from 100 nanograms or higher, 5 or 10 minutes may be quite enough. Then you pull it down on the magnet. The amount of time you need to pull down on the magnet depends on your magnet and the tubes you use. On the robot specifically, we normally find, so with the black magnets that we use on the robots and standard PCR plates, 3 minutes is normally enough to pull down, and you really want the supernatant completely clear, so it mustn't have sort of a brownish tint. It's nice that the ampere is brown, so it's easy to see when everything's pulled down. But because this is a large reaction and because it's a very viscous reaction, be careful, the pull down time, the optimal pull down time for this step may be a little longer. So sorry, one thing I forgot to say, the reagent mixes in this kit, because the chemistries are additive, the buffers are more concentrated, the enzymes are more concentrated. So you will find with the HyperPrep kit, as far as handling is concerned, the enzyme mixes, reagent mixes are a little more viscous than what you would be used to. So just make sure that when you're pipetting, pipette nice and slow. Try not to get bubbles, blown into things. Not a huge problem, but just look out for it. It is pretty viscous. These solutions are pretty viscous. So now you've pulled down on the magnet. You remove the supernatant. You're going to add some ethanol. The only thing that the DNA is now bound to the beads that the magnet's physically holding down. All that the ethanol is there is really to wash away some excess salts and things like that. And literally there's no washing. You just pipette a little bit of ethanol. Always try and cover the beads. I mean, we just routinely say 200 microliters, but anywhere between 150 and 200 microliters is sufficient to make sure that the beads are completely covered. And you just leave it there for 30 seconds. So it stays on the magnet. You don't resuspend or anything at that point. You just leave it there for 30 seconds, pull off the ethanol, put fresh ethanol on for another 30 seconds, and use 80% ethanol. Make the ethanol fresh. You don't have to make it fresh for every step, but fresh in the morning. So don't use ethanol that's been standing on the bench. The binding of DNA to ampere beads, because ethanol is it's a hydrophobic solution instead of hydrophilic where your buffers are. It doesn't make the DNA come off the beads, but if your effective ethanol concentration drops below 70%, then it is going to start leaching the DNA off the beads and you're going to lose it in the washers. And so use 80% ethanol, make sure it's fresh every day. And then after the second wash, I mean, some people are saying, oh, well, we're going to dry the beads anyway, so I can leave a little bit of ethanol. Try to get all the ethanol off, because if you over-dry spry beads and they've kind of become cracked, they do lose their potency, and you can lose some of your DNA. So our approach here is, whenever you're removing supernatant, don't think you're going to dilute it in the next step, or you can compensate in the next step. Try and be careful and always remove all supernatant. So whether it's supernatant before ethanol washes or ethanol before drying, make sure it's all off. And then drying, 3 minutes at room temperature should absolutely be fine. We don't recommend drying the beads at 37 degrees. They should not look dry and cracked. They should still have sort of a little bit of a glisten, like a sheen to them. Then you know that they're still in good shape. And then we're eluting. Typically, we like to always keep DNA in a buffered solution. So at this point, eluting 10 millimolar tris or EB buffer. Everybody should be familiar with that, 10 millimolar tris, pH 8 or 8.5. And then depending on what comes next, it depends on the elution volume. So for library amplification, you can put a maximum of 20 to 24 microliters of DNA in that reaction, depending on how your primers are formulated. So around 25, we normally eluting 25 microliters, take 20 into the PCR. Then you still have a little bit left for post-ligation QC if you need to. And if you're going to size selection, then you're going to use 55 microliters. We just increase for spray bead manipulation. It's always better to work at least, have your sample in at least 50 microliters. Otherwise, it kind of gets a little hard to handle. The library amplification, pretty straightforward. So the hi-fi ready mix is a 2x ready mix. So in a standard 50 microliter reaction, you're going to use 25 microliters. If you're using the library amplification primers that we supply in the kit, so this is, remember again, for libraries that have P5 and P7 sequences at the end of so made with complete adapters, they're formulated to be a 10x mix, so you're going to use 5 microliters, which leaves 20 microliters for your adapter ligate library. If you have a really, really low input applications, you can push this, and you have a custom primer mix, you can push this to 24 microliters and a microliter to really get as much as possible in this reaction. But this is an extremely efficient reaction, and so with these standard conditions, you should get good results. Primer concentration is very important. The kit supplied primers end up at a concentration of 2 micromolar of each primer in the reaction. If you're going to be using your own primers, make sure it's in the range of 0.5 to 2. For anything more than 100 nanograms into library construction, you need to use at least 2 micromolars of primer in the reaction to make sure that you don't get primer depletion. Cycling parameters are very standard hi-fi reaction, so we have a short initial denaturation. This is not complex genomic DNA, so we don't need a lot of time up front to denature the DNA, so you don't have to do 2 or 3 minutes as you would do for normal PCR. Very important, hi-fi is a B family enzyme, has a lot of salts in the buffer, and so you have to denature at 98 degrees, not at 95 degrees. Standard annealing at 60 degrees, this is for kind of the standard Illumina adapters and primers. If you have a very strange adapter design and primer design, you may have to optimize annealing temperature. But 60 degrees should be definitely works for the standard 2-seq designs. And then your extension for 30 seconds, that's enough for library construction. You do a final extension of 1 minute. And then how many cycles do you do? So there are 2 tables in the TDS that provide some guidelines for this. So table 4, you can, based on your input into library construction, so that's the amount of DNA that's going into the fragmentation reaction. It tells you, like, if you're trying to make 100 nanograms of library, and this is sort of the ballpark that you'll be aiming for if you're going directly to sequencing. If you're going direct to target capture, you're going to be aiming to make around about a microgram. So it could be, in the range of a half nanogram to a microgram to 2 micrograms. This could be in the range of 50 to 150 nanograms. But again, if you only need 100 nanograms of DNA, don't try and make 5 micrograms. This reaction can actually make 10 micrograms of DNA if it's fully optimized. We don't recommend that. There's no application where you need 10 micrograms of DNA. So again, pick the number of cycles, based on your input into library construction. And this is sort of, this is determined based on expected conversion rates for good quality DNA. For FFPE, for instance, you may need a few more cycles. So this is a good starting point. Pick like the middle of the range and see where you're at. And then, in some cases, obviously, if you start library construction with a microgram of DNA and you go straight to sequencing, you should not have to amplify. You should have a lot more than 100 nanograms of DNA. But in some cases, if you have an incomplete adapter, you may have to do a few cycles of amplification to complete your adapter. And then, so this is the one way of using the table and figuring out as a starting point at least how many cycles of amplification we need to do for your first evaluation. The other option is to stop, do the post-ligation QC, and then you know exactly what you have. So where this input is the input into fragmentation, this is the actual amount of DNA that goes into the amplification reaction. And so if you have quantified that, then this gives you the cycle numbers for around about a microgram of DNA, and if you need 100 nanograms, it's about 3 cycles less. And so that's the other way. This approach is a really good one for when you try the kit for the first time. You're going to do a couple of reactions with different fragmentation times, to determine your fragmentation parameters. Just pick kind of the middle of this range, and then optimize your library amplification in a second stage once you've optimized your amplification parameter, your fragmentation parameters. And so the post-PCR cleanup, very simple. The ratio here is 1x instead of 0.8x. Your total volume is 100 microliters, so it's smaller than the post-ligation cleanup. Very easy to work with. Everything else is pretty much the same because the volume's a little lower. The pull down time should be a little less. You can get away with a little less. The only thing that's important when you elute here, it depends what you're going to do next, what volume you should elute in. And so if you're going straight to sequencing, if this is obviously a final library, some people want to store the library. Remember, DNA is most stable the more concentrated it is. So don't elute in 100 microliter and unnecessarily dilute your DNA. Normally like somewhere between 25 and 50 microliter, 55 microliter is a good elution volume. You're going to lose a little bit in the final transfer, so you normally recover 5 microliters less than what you elute in. But if you're going to target capture, you may have very specific recommendations depending on your target capture protocol. And very important, unless you're going to target capture, always elute in a buffered solution because that's best for storing DNA. But if you're going to target capture, hybridization protocols normally have a dry down step where you basically dry your DNA, you concentrate your DNA in a speedy vac. If you have salt in your solution, that takes hours. And so only for target capture and only after the post-amplification, for the post-amplification cleanup, you have to use water at that point. And so here's just some practical examples. So these are 2 libraries made from either 10 nanograms or 100 nanograms of human genomic DNA. So these 2 libraries, the green one is the 10, the red one is the 100. And for the longer insert libraries, the turquoise one is the 10, and the darker blue one is the 100. And so this was made with the reaction setup. There was no EDTA in this reaction, so it's just the input, either the 10 or the 100 nanogram was just diluted into 35 microliters with EB buffer. Everything set up as per the standard conditions. This one was fragmented for 30 minutes, so we were trying to kind of get around about 150 base pairs average fragment size. When you add adapters, the 2 full-length adapters add up to about 120 base pairs. So you see we kind of achieve a mode fragment size just over 250 base pairs, or in the range of 270 base pairs. These libraries were fragmented for a little shorter, so the fragmented DNA ended up being a little longer, around 250 base pairs. And so once you add the 120 base pair adapters, they end up around 370, and this is after amplification. So for the 100 nanogram input, just straight according to the table, did 6 cycles of amplification. The 10 nanogram input, 12 cycles of amplification. Sorry, so there's a 10 here and a 10 there. You can see there's a little bit of that sort of high molecular weight bump that we talked about before, and so probably could have done a few less cycles of amplification in there. In the last part of the QC, I want to show you how the Kapa library quantification kit works. This is the qPCR-based kit for quantification, and just because many of you may not be familiar with qPCR or qPCR-based quantification. So it's essentially a kit that allows you to do absolute quantification by qPCR. And very short, in short, you get a qPCR master mix, you get a primer premix, which again targets the P5 and P7 primer sequences or adapter sequences. And then, so that's all the reagents you need for the qPCR part. And then it has 6 DNA standards. So this is a pre-diluted standard that performs a 10-fold dilution series. The first standard is 20 picomolar, and the 6th standard is 0.0002 picomolar. The reason they're in picomolar is that's what that's the concentration in which you measure your, assess your library for cluster amplification in the end. As we said previously, typically your libraries need to be somewhere between 2 and 10 nanomolar before you get to library amplification. So the first thing that's important is that you're going to have to dilute your libraries to get them into the dynamic range of the assay. The reason we made the standards fairly dilute is it does allow you to assess PCR-free workflows, so where your libraries are much less concentrated, or libraries made from really low inputs very accurately by qPCR. So essentially, you set up the qPCR reaction. It's very simple. You have 12 microliters of PCR mix, 4 microliters of primer, 4 microliters of DNA, whether your DNA is a standard or a diluted library. You do the PCR, it's a 35-cycle PCR, and then you get obviously a CQ score for each one of your standards and then each one of your libraries. For absolute quantification, we plot the log of concentration against the CQ score. Sorry, that fell off the axis here. And it gives us a straight line with a negative slope. So obviously, the higher the concentration, the lower the CQ, and the lower the concentration, the higher the CQ score. And so, because we have a ruler now, we have a set of standards that relates concentration with CQ score. When we have the CQ score of an unknown sample, we can read from there the log of concentration. And actually, so we have a very nice data analysis template, which you can either download from our website or request from support. And it gives you, some of these calculations you can do with your qPCR software. Some of it you can figure out in Excel, but we just built a nice Excel spreadsheet to help you through this process. So in the first part, what you're going to do is put the concentrations for the standard. In fact, it's pre-populated, it's already in there. You're going to put the CQ score, so everything, because it's qPCR, it's very sensitive, everything is set up in triplicate. So you basically look at the values. There are rules, and we explain them on how to throw outliers out. So if you have triplicate reaction, and essentially anything that's more than sort of 0.2, 0.25 of a cycle away from the other are outliers, we know that there's experimental variation, and so we throw them out. That's why we do triplicates for confidence in the data. And then what this table does is it works out the average CQ score for every standard, and it also looks at the delta CQs. So if you know qPCR pretty well, and this is just a general rule really for PCR, if you have a 10-fold dilution series, you would expect 3.3 cycles difference between every subsequent dilution. And it's basically because 2 to the power of 3.3 is 10. And so if you had perfect exponential amplification, which this assay is designed to be able to do, you would, the delta CQ, the difference in CQ score between consecutive standards should be around about 3.3 cycles. So anything between 3.2 and 3.6 is good. And these blocks will turn red if you're outside that range. All that it does is, because we supply you a perfect set of standards, if you're seeing that these delta CQs for any two of the standards are kind of out of range, it is an indication that there's some, there may be some experimental error or inaccuracy. Because remember, you're drawing a standard curve here. If your standard curve is not good, then any calculations you're going to make from the standard curve aren't going to be good. And so that's the other nice thing about qPCR as a quantification method. It just has a lot of inherent metrics built into it that you can tell whether you're doing a good job and whether it's likely that your calculated concentrations are going to be accurate or not. So, depending on these blocks, if everything's out of range, we definitely have you repeat, recommend you repeat the assay. If everything's kind of, all these delta CQs are in the range of 2.5 to 2.6, you're good. 3.25 to 3.6, you're good. And then no template controls, we do recommend you put them in. And the delta CQ between, template controls and standards, it should be at least 3 cycles. And so that's, in most cases, it's way more than that. Then what the second part of the spreadsheet will do, it'll take these average CQ scores, which you've just worked out, and it'll draw the standard curve for you. The Excel works out the coefficients for the curve, so y equals ax plus b with the graph. It also works it out with some formula, so you can double check. So the slope value that's worked out here from the is worked out with a formula should be the same as in the graph, and also the intercept. The intercept you have to type in this block, and the slope you need to type into this block. It also works out the reaction efficiency, which is the reaction efficiency, that should be between 90 and 110%, preferably between 90 and 100%. And it works out your fit. So your fit needs to be between 0.99 and 1. And if all of those conditions are met, you have a good standard curve, and you can continue. Whatever you're going to be calculating off the standard curve is going to be accurate. And so what the next step of the process does, you're going to put your sample names in. Very important, you have to put the dilution in of the dilution you made to get the start, before to get the samples within the dynamic range of the assay. And for post-ligation libraries, somewhere in the range of 5,000 to a 10,000 dilution normally gets you in the range. For amplified libraries, somewhere between a 1 in 50 and a 1 in 200,000 dilution gets you in this range. And the instructions for this kit actually provides really good guidelines for that. So again, you put your CQ scores in, you put your fragment length in, so this is what comes from your bioanalyzer, and then it works out to get your average CQ scores, provides guidelines for throwing out outliers, and then it works now out. So remember, the standard curve plots average CQ, which is the thing you measure, versus log of concentration, which is what we know for the standards. And so for your unknowns, it's going to take the CQ score, work out the log of concentration using the parameters for the straight line. And then it's going to work backwards. So it's going to work out the log of concentration, the average concentration from the replicates, the size adjusted concentration, and this is why you need the size. And this is just because a cyber is a mass-based calculation. So you have longer molecules. If your library is longer than the standard, which is 450 base pairs, it's going to bind more cyber. If it's shorter than the standard, it's going to bind less cyber, which affects the CQ score. And so this is just a proportionate calculation. It just takes the concentration that was worked out and multiplies it by the length of your library, the average size of your library, by the length of the standard. Then it works out the concentration, so it takes the dilution factor into account, works out the concentration of your undiluted library in picomolars, in nanomolars, in nanograms per microliter, so you have all the different sort of units of measure you need. And then in the next, there's a second sheet where you then can put in the volume of your final library, and again, it will work out for you what the yield of library was. So in this specific example, from the table, we pick the number of amplification cycles for the 100 nanogram inputs and the 10 nanogram inputs. That should give us round about a nanogram of, this should be round about a microgram, so just over 1,000 nanograms of library. You can see this one, because the yields, the library yields were actually higher. We could have probably dropped the cycle of amplification on that one. Not a crisis, but it shows you the value of doing these calculations so that you can really optimize especially for precious samples. And then if you work back from this, you could kind of, assuming a certain amplification efficiency, you can kind of work back from this. And again, we have another calculator that we designed to do this. Please contact us. We're happy to share it with you. And we could working backwards from the post-amplification yield. We estimate that the conversion rate, so the amount of input DNA converted with that like-rated library, was somewhere between 40 and 50% for the 100 nanograms and 20 to 25% for the 10 nanograms, which is nicely in the range that we would expect. And so the conclusion is that this is first time off. This worked really, really well. If we have 100 nanogram inputs, there's probably no reason to optimize things much further. For the 10 nanogram inputs, maybe we can look a little bit at adapter concentration and see if there's a benefit if we use more, or tune down the amplification cycles if we don't really need all that much. But pretty much with standard conditions, it's possible to get a good approximation the first time around. So to summarize, HyperPlus Kapa HyperPlus kit is a very efficient library construction kit for quick production of Illumina libraries. So very versatile. You can use it for a wide range of inputs, different sample types, different applications. Your library construction process is going to be somewhere between 1.5 and 3 hours, depending on whether, how long your fragments for, so what your target fragment size is, and whether or not you're doing amplification. Library amplification conditions, we've really provided as much help there as we can to make it optimal. And really, there's very few parameters to optimize. So upfront, the trick is just to figure out how to do your fragmentation to get right on spot on what you need for your application. And then maybe you can look at adapter concentration and cycle number depending on your sample type and input.